In this video, electric fields will be explored. Electric field and electric field strength will be introduced, and a test charge will be used to draw the electric field due to point charges. Secondly, field lines will be drawn to visualize electric fields due to two opposite charges and two like charges. The electric field strength formula will be explored, and the electric field strength for a point charge formula will be derived and applied for fields created by two charges. Finally, the electric field due to charged parallel plates will be discussed, including the formula for the electric field strength. We will also look at the motion of a charge in the field. An electric field is an area in space in which a charged object will experience a force. Test charges, small positive charges, are used to define the strength and direction of the electric field. Each point in a field has a vector quantity called the electric field strength, capital E. The electric field strength is defined as the force per unit charge on a positive test charge placed at the point in the field. This definition can be expressed mathematically through the formula electric field strength E is equal to the force F divided by the charge Q. The direction of the electric field strength at a point is defined as the direction of force acting on a positive test charge placed at that point. Note that the test charge is a small theoretical charge that has no impact on the field itself. If we consider a positive point charge, placing the test charge at a point near the charge shows a repulsive force acting to the right. If the test charge is moved along this line, the force remains to the right. The electric field line can be drawn as an arrow pointing to the right along this line. If the process is repeated for other locations, the electric field due to a positive point charge can be drawn. Through the same process, the electric field due to a negative point charge can also be drawn. These are both described as radial fields. Electric field lines never cross each other, always coming out of positive charges and into negative. The spacing of electric field lines reflects the strength of the field. Where field lines are close together, the field is strong. More complex fields can also be drawn. For example, the field created by an opposite dipole of equal magnitude. Each charge has an electric field. So the net electric field created by the two charges will be the vector sum of each field. If a test charge is placed between the two charges, there will be two electrostatic forces acting on it, both in the same direction. The electric field at this point will be the vector sum of these two electric field strengths. If the test charge is moved along this line, the electric field will remain pointing to the right. If the test charge is placed at another point in the field, the two electric field strength vectors can be added to find the direction of the electric field at that point. By placing the test charge in many points and adding the two electric field vectors, the net electric field vector for the field can be drawn. In the overall pattern, we can see the curved shapes of the field lines emerge, again with the spacing of the field lines reflecting the strength of the field at different locations. Through the same method, the electric field due to a dipole of like charges of equal magnitude can be shown. Each point in the field will have an electric field strength equal to the vector sum of the two electric fields. By moving the test charge to different points and adding the electric field vectors at these points, the net electric field can be drawn. Note that the pattern for two equal negative charges would show the same shape, but differ in that the arrows on the electric field lines would be pointing in the opposite direction. A positive point charge, Q1, will create an electric field radiating out in all directions from the charge. The electric field strength at a point a distance r away from the charge is given by the formula electric field strength E is equal to the force divided by the charge. Coulomb's law can be used to quantify the electric field strength at a distance from this point charge. If a charge Q2 is placed at this point, it will experience an electrostatic force described by Coulomb's law. By substituting Coulomb's law into the definition of electric field strength and canceling out the magnitude of the charge Q2, the relationship for the electric field strength of a point charge can be derived. In this formula, K is Coulomb's constant, 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. Q1 is the magnitude of the point charge creating the field, and R is the distance from the charge to that point. Important to note that this expression is limited to electric fields created by point charges, although uniformly charged spheres can be approximated to act as point charges with all of its charge assumed to be concentrated at its center. Note that the electric field strength due to a point charge is inversely proportional to the square of the distance from the charge. Consider the electric field created by a dipole of two opposite charges of equal magnitude. The net electric field at a point is the vector sum of the electric fields due to the two charges. If we consider the midpoint between the two charges, when we add the fields from the two charges, both vectors are pointing in the same direction. So the net electric field strength at this point is the sum of the two. If the point in question were to be shifted up from the midpoint, the electric field vectors are no longer pointing in the same direction, and the net electric field vector must be found by using two-dimensional vector addition. There can exist points in a field where the net electric field strength can be zero. If we consider a field created by a dipole of two equal negative point charges and examine the midpoint of the line connecting these charges, the two electric field vectors are equal in magnitude but opposite in direction. The net electric field strength at this point will be zero, and a charge placed at this point will not experience a net force. If the magnitude of the charges is not equal, then the point where the electric field strength is equal to zero will shift away from the charge with the greater magnitude. An important electric field in physics is the one created by charged parallel conducting plates. Two charged parallel conducting plates will have a potential difference between them. These charged plates will create an electric field pointing in the direction of the positive plate to the negative plate. This field is uniform throughout the area between the two plates. Theoretically speaking, the field is only uniform if the distance between the plates is small in relation to the area of the plates. This field will not exist outside the plates except for a small edge effect where the field lines will be curved just at the edge of the area between the plates. Using the definition of the electric field strength is equal to the force per unit charge acting on a positive test charge. We can find the expression for the force on a charge placed in the uniform field between the plates. The electrostatic force will equal to the electric field strength times the amount of charge Q. Because the electric field strength is constant, the force acting on a charge within the field will be constant, and its acceleration can be calculated using Newton's second law. If a charged particle traveling at a constant speed enters the plates perpendicular to the field, the force acting on it will be constant. The charged particle will follow a parabolic path and undergo projectile motion within the field. If we consider a proton and an electron entering the field horizontal with equal velocities, the force acting on the proton will point towards the negatively charged plate, in the direction of the electric field lines. The force acting on the electron will point towards the positively charged plate, in the opposite direction of the field lines. The force acting on the charges is equal to the electric field strength times the charge Q. And because both particles have equal charge, the force is the same for both. But the mass of the proton is much higher than that of the electron. The proton has a mass of 1.6 times 10 to the negative 27 kilograms, whereas the electron has a mass of 9.11 times 10 to the negative 31 kilograms. So the acceleration of the electron will be larger than that of the proton. This can be seen in the relative paths that the particles will take as they enter the field. The work done in moving a charge from one plate to the other can be calculated using the formula work is equal to force times displacement, where the force needed would be the electrostatic force equal to the electric field strength times the magnitude of the charge Q. So the work done in moving the charge from one plate to the other would be equal to the electric field strength E times the magnitude of the charge Q times d, the distance between the plates. The definition of potential difference is the ratio of the work done in moving a charge to the amount of charge. Potential V is equal to work W divided by Q. Subbing the equation for the work done into the definition of the potential difference and simplifying, will yield the electric field strength of the parallel plate electric field. The electric field strength E is equal to the potential difference, delta V, divided by d, the distance between the plates. In summary, an electric field is an area in space surrounding a charged object which can exert an electrostatic force on another charged object. The electric field strength at a point in the field is defined as the force per unit charge acting on a small positive test charge in the field. The direction of the electric field is defined as the direction of the electrostatic force acting on a positive test charge. Some key fields include the electric fields of point charges, including the positive point charge and the negative point charge, unlike dipoles of equal magnitude, like dipoles of equal magnitude, and like dipoles of unequal magnitude. The electric field strength is a vector quantity and has units of newtons per coulomb. Around a point charge, the electric field strength is given by the formula electric field strength E is equal to Coulomb's constant K, 8.99 times 10 to the 9 Newton meter squared per Coulomb squared, times the amount of charge Q1 that is creating the electric field, divided by the distance r to the point in the field. For fields created by multiple charges, the electric field strength at a point can be found through the vector addition of the individual electric fields. In some places, this vector addition can result in an electric field strength of 0 newtons per coulomb. The electric field strength due to oppositely charged parallel plates is uniform between the plates, with a field strength given by the equation electric field strength E is equal to delta V, the potential difference between the plates, divided by d, the plate separation. A charged particle placed in this electric field will experience a constant electrostatic force pointing towards one of the charged plates. If the charge has a velocity perpendicular to the electric field lines, that charge will move in projectile motion. This concludes our survey of the topic of electric fields. Thank you for watching.